Okay, so in the last video we discussed about test paths and what is meant by visiting and what is meant by touring. In this video we are going to discuss about tests and test paths. So when we use the notation path and this small t, it means a test path that is executed by a test t. By small t we mean a data value that can be input to the program and that possibly will give us some output. And this path capital T is another notation which means the set of test paths executed by the set of tests in T. So capital T basically consists of some set of some test cases, some set of tests. And it is also important to note that each test will execute one and only one test path. Means when I give an input to a program, so that definitely is going to exercise just one path on the graph of that program. And further, it also means that when we input the value, the execution will start in terms of the graph from a start node and it will end on a final node if the program is terminating. So another definition which we need to know about is a location in a graph, either a node or an edge, can be reached from another location if we have a sequence of edges from first location to the second location. Means a location can be connected to another location by a sequence of edges, and such a connection by means of edges, by a sequence of edges, is either called a syntactic reach. So it means a subpath exists in the graph from the first location to the second location. And there is another notion of a reach that is called the semantic reach, and by that we means that we have a test that actually will execute a subpath between the two locations which we just identified that are connected by a sequence of edges. So there is an interesting relationship between the tests and the test paths. So generally it is the case that a test path may be exercised by one or more tests. So, but each test will actually exercise just one test path in such a scenario, and when that happens, we call that software to be a deterministic software. So in this case, test always executes the same test path. But there are certain software where this kind of relationship does not hold, and in that case a test may execute several test paths. For example, if you see here test 1, it can execute test path 1, it can execute test path 2, and it can execute test path 3, and in the same way the test 2 and the test 3 can also execute test path 1, 2 and 3 depending upon the scenario. When that is the case, when we can execute different test paths by one or more test cases, then such a software is said to be non-deterministic software. In such a case, a test can execute different test paths. So in the context of testing, we are interested in covering certain sections or parts of the graph, and that we want to do by means of our tests. So we use graphs in testing as follows. First, we develop a model of the software which is in the form of a graph, and then we want our tests to visit certain parts of the test graph, like nodes or edges or some subpaths or edge pairs and so on, and we want to see how much of those nodes or edges have been covered by our tests. So then we have some definitions. First of them is the test requirement, and what do we mean by that? A test requirement is a property of a test path. So a property which a test path must fulfill, that is captured in the form of a test requirement. And then another concept is of a test criterion. What do we mean by that? These are basically the rules that define the test requirements. And then there is a satisfaction relation. What do we mean by that? Given a set TR of test requirements, which we just defined here, for some criterion C, then a set of tests T satisfy this criterion C on a graph if and only if for every test requirement in this TR. Just remember that TR may have more than one test requirements. So there is a test path in path T. We defined this path capital T on the previous slide, which means set of paths that are exercised by the set of tests in this capital T. So if for every test requirement we have a test path in path T that meets the test requirement TR, then we say that the criterion C has been satisfied by this particular set of tests in capital T. So we have the notion of the structural coverage criteria, and we have the notion of data flow coverage criteria. The structural flow coverage is defined just in terms of nodes and edges on the graph, and the data flow coverage criteria has a specific requirement that the graph must first be annotated with the references to variables. And what do we mean by that? We define variables, and we have the uses of those variables. So this kind of a graph will be annotated where a variable is defined and where a specific variable is used, and then we try to find what sort of definitions of the variables reach which uses of that particular variables. So the two very simple coverage criteria in terms of structural coverage are node coverage and edge coverage. So the first one is the simplest one, which is called a node coverage. It is denoted by NC. And what is the definition of this coverage? A test set T satisfies node coverage on a graph G if and only if for every syntactically reachable node n in n there is some path P in path T such that P visits n. So what do we mean by syntactically reachable node? It means there is a path or there is a sequence of edges that go to this node n in the graph, and this path T we already defined that it is the set of test cases in T that exercise some paths, and those are included in path T. And if we have those parts which exercise the nodes in the graph, then we will say that the node coverage criterion has been fulfilled by this set of tests in T. Or simply put, we can also say that test requirement contains each reachable node in G. So it is important to note here that there might be some nodes which are in the control flow graph of a program which are not reachable from the initial node. So such unreachable nodes will not be excluded in the node coverage criterion, because we can never exercise such kind of nodes. So the next criterion is the edge coverage criterion. And what do we mean by that? Test requirement contains each reachable path of length up to 1 inclusive in G. So now this is rather interesting. So why we have used this length up to 1 and inclusive in G? So the phrase length up to 1 allows for graphs with node and no edges. So we have included this length up to 1 phrase to include those graphs which have just one node and they have no parts of the length more than 1. So in that case, why we have included this? Because we want our coverage criteria to be included in other coverage criteria, and in terms of testing we called such kind of relationship as the subsumes relationship. What does this mean? That one coverage criteria when it is included in another coverage criteria, we say that the first one is subsumed in the second one. So In this case, we will just see in this example, that when we fulfill edge coverage, then that automatically achieves node coverage. So we'll say that edge coverage subsumes node coverage. So are only different, edge coverage and node coverage are different when there is an edge and another subpath between a pair of nodes. So if there is a branch in the graph from one node, there are two branches, then we would say that edge coverage and node coverage will be different, and that typically reflects a conditional statement in the code of a program. So if there are no conditional statements in the program, then in that case, node and edge coverage will be the same. So here we see a simple graph. So here we have node 1, and we have two edges going out of node 1 to node 3, and another one from node 1 to node 2, and then we have an edge from node 2 to node 3. So in this case, node coverage will be to cover all these nodes 1, 2 and 3. So if we exercise just this path 1, 2 and 3 as written here, we can achieve node coverage. So you just need to notice the test requirement has curly braces. It means it is a set of nodes. We cannot duplicate nodes when we are using curly braces, and it notates a set. And when we have the path, we write the nodes in a path, or the sequence of nodes in a path, in square brackets. So when we use square brackets, it allows that some nodes can be repeated. We will see that when we cover the topic on loops. Now, in the same way, when I try to find out the edge coverage on this graph, what I have to cover is, or the test requirement is to cover edge 1, 2, cover edge 1, 3, and the cover edge 2, 3. And you can see that this cannot be achieved by just having this test path. If I just execute this path or traverse this path 1, 2, 3, I am going to miss out this particular edge 1, 3. So for that, I have to add another path, which is from node 1 to node 3 in my set of test paths, which is written here. It also includes the first path, and it also includes the second path we just identified. So now this set of test paths 1, 2, 3 and 1, 3, this covers, or this achieves edge coverage on this simple graph. And here you can also see that this set of test paths given below is actually containing the set of test paths given for the node coverage. So here we can clearly see that the test paths for edge coverage contain the test paths for node coverage. Therefore, we say that edge coverage subsumes node coverage. Okay, that is all for this lecture. I will come with a new topic in the next video. Thank you.